Ladies and gentlemen, a warm welcome to all members joining us from various corners of IEEE Region 10. I'm Baranika Hippola, the student representative of IEEE Region 10, and it's a pleasure to have you all here with us today. So, as we gather for the third R10 talk of the year 2024, let's embark on yet another insightful journey together. R10 Talk stands a collaborative effort among several committees within IEEE Region 10, where we delve into discussions surrounding cutting-edge technologies and scientific advancements and innovative ideas, and also motivational insights. So today we are excited to present another captivating topic. So without further ado, to introduce our esteemed speaker and extend a heartfelt welcome to each of you, it's my honor to welcome Professor Akinori Nishihara, past director of IEEE Region 10 and also an emeritus professor at Tokyo Institute of Technology. So Professor Akinori.
Yeah, thank you, Veronica.
Over to you.
Yeah, thank you very much for coming to today's R10 talk. We are happy to have Professor Fakhrul Alam for today's speaker. I will briefly introduce him. He is a professor at the Department of Electrical and Electronic Engineering, Auckland University of Technology, AUT, New Zealand. He received his Bachelor of Science with first-class honors in Electrical and Electronic Engineering from Bangladesh University of Engineering and Technology, BUET, and his Master of Science and PhD in Electrical Engineering from Virginia Tech, USA. Professor Alam is a leading expert on indoor localization and human sensing for smart homes and buildings. His research integrates sensors, the Internet of Things, and machine learning to enable robots and individuals to navigate while utilizing the existing wireless and lighting infrastructure of buildings. Professor Alam's research also has direct applications to assisted living, aged care, human-machine interactions, and environmental monitoring. His research work has received funding from the likes of the New Zealand Ministry of Business, Innovation and Employment, Auckland Transport and New Zealand Forest Research Institute Limited. Professor Alam is a senior member of IEEE and sits on the IEEE Conference Technical Program Integrity Committee and IEEE Conference Application Review Committee. He has served as an associate editor of IEEE Access and a reviewer for the Royal Society Te Aparangi. He is a regular invited speaker at various national and international forums, and he's led, for example, General TPC Program OC Chair, the organization of many international conferences. Okay, so let's invite Professor Alam. Thank you.
Thank you, Professor. I hope everybody can hear me. It's a very warm welcome to everyone. Currently, I'm in New Zealand. I'm sitting at my home office, which also is my bedroom, and it's about 10 o'clock. But it's exciting times because I get to sort of talk about something I'm very passionate about, and that is human sensing in smart homes and smart buildings. So if you just give me a little bit of time, what I'll do is I'll share my screen, and hopefully we can take it from there. So I'm hoping that everybody can see my screen. Okay, fantastic. And I also apologize if I seem to be, looking in a different direction and not making eye contact, because I have three screens in front of me. So I'm looking in one direction and presenting from somewhere. So thank you very much for the kind introduction. And my talk is going to cover pretty much the human sensing umbrella, and and I will draw from my own research experience, and hopefully, you will get a good idea about what exactly is this and what's the current state of the art, and if you really want to get interested, then what would be the future direction of this particular discipline. So first of all, when we say human sensing, it actually, sort of encompasses quite a few things. So starts from the very simple is presence or occupancy. So the fundamental question is somebody here? If somebody is here, then maybe we can take some actions. So this is something that is very commonly currently used in any modern buildings. So you have appliance, sorry, you have HVAC, lighting, and that kind of sort of systems that get controlled by very simple motion detectors. So if somebody is there, maybe the lights will turn on, and if there is nobody present at some point, the lights will turn off. So it's quite simple. The technology has been there for a long time, and it is, but it is quite important, because that way you can save energy. I'm just giving you one example. So, and then count. So the next thing of after presence and occupancy is basically count. So how many are here? So depending on how many are there, maybe you can sort of give some type of service or arrange something depending on how many people are there. Or maybe you just want to know how many people actually pass through a corridor or something like that during evacuation. So is somebody here? How many are here? And then the next thing you would want to know is the identity. So who are these people who are there? So if you know who they are, then maybe you can give sort of very personalized service depending on who that particular person is. Okay, and then the next thing that you would want to know is positioning. So where are they? So depending on where they are, you can. So for example, somebody is standing in front of a mirror, and maybe this is morning time. So basically what you say is maybe you turn the backlights on, and sort of turn the heater on. Who this person is. So if there is anything that you want to customize, you can customize. And then the final thing would be gesture recognition. So maybe they are doing some gestures with their hand. Based on that, you interpret that, because you want to, I don't know, control the volume of your television or something like that. Very simple. What activities are they doing, or what, some sort of an event. So one of the things that people are often interested in is, especially for aged care, is has someone fallen down, has someone suffered some sort of an accident or not. Or you are looking after somebody, an older adult, and you want to know whether that person is active or not, because if that person is active, that means probably everything is fine. So those are the five sort of main things of human sensing. So I always sort of bring us to this concept of GPS. Everybody knows GPS now. Of course, GPS was for precision, sort of positioning. But once that infrastructure has been made open to public, so many applications have come forward, because we have so-called free infrastructure. So when I discuss about human sensing, I believe that the ethos should be like that, rather than sort of deploying sort of dedicated infrastructure for this purpose. What you actually would want is, you already have an existing system, and you want to leverage that uh, to sort of get secondary service that is human sensing. Now, as we said, one of the important, sort of applications of human sensing is localization or positioning. Even though we have a very mature technology like GPS doesn't really work well in indoors, because, if satellite signals don't really, sort of survive very well, when it has to penetrate, sort of buildings. So even if you just wanted very simple positioning, you cannot rely on GPS when you are, inside, a built environment. So I'm not going to spend a lot of time on what are the applications. I want everyone to sort of think about what the applications could be, because it's that the whole point is you actually understand what human sensing is, and then I want you to think about what could be my application. How can I leverage that and do something that I'm passionate about? But in broad sense, one of the major areas of human sensing is ambient assisted living. So basically, we are, as population globally, getting older and older, but we still want to live independently, and this technology is actually sort of tailor made for that. Any kind of human to machine interaction, human to computer interaction, you would want this technology. You want to know where they are, what are they actually gesturing, so that you can actually interact with a machine without sort of contact. Safety and security, if you can identify people, and then you see, okay, all of a sudden somebody has entered this building, and I do not recognize that person, so maybe it's an intruder, and maybe you can sort of take some safety measures. And then there are a lot of sort of applications in terms of energy consumption, having very sort of energy efficient buildings by customizing services. But I've just given you only the tip of the iceberg. My point is, you look at the technology, and then you think, how can I leverage that? Okay, so in sort of broad terms, human sensing, there are two different types. One is active and the other one is passive. So active is when the subject is carrying some sort of a device. Now, this is why it also kind of goes into indoor localization discipline, in the sense that if that target is not a human, then if maybe you are trying to position a robot, maybe you are trying to position trying to localize some sort of an asset in a large warehouse or something like that. One of the problems that I got I faced when I started working on that was in New Zealand hospitals. There are a lot of equipment, and then that particular, let's say, a drug infusion pump, there are 200 of those. But when you are looking for one of them, you cannot find them, because last time somebody used that, they were taking a patient to the operation theater. They were not really worried about what's going on with the drug infusion pump. They just left it there and ran with the patient. So a lot of those sort of assets oftentimes go missing. And if you had some sort of an asset tracking system, almost like a GPS tag in indoor, then that would be an application. But we are not sort of talking about that. Our goal is still the target is a human subject. So for those ones, a tagged or an active system would be, if you are carrying a smartphone, then basically that smartphone or some sort of wearable device, based on that, either the system is trying to position you, trying to recognize you, or trying to understand the activities that you are doing. Okay, and then you have an untagged, sort of uh, uh, human sensing system, where the subject is not carrying any device or any tag or anything like that. But at the same time, we want to make sure that we can either localize this person, we know who this person is, we know where this person is, and then we can interpret the gesture. Now, for active human sensing system, motion capture systems that are quite popularly used in sort of in the movie industry. So where they are using camera, and then they are putting sort of tags on you, and then from there, they can do very precise reconstruction of your activities. Oftentimes, actors perform, with these things in front of a green screen, and then they use, special effects and CGI and all sorts of things. But to be honest, when we are looking at passive, untagged human sensing, robust solutions, we are still a little, sort of not that matured. It's still a little bit, sort of under development. So there are no um, accepted or a universal solution um, for device-free or untagged human sensing, um, especially techniques that are very robust and can work in real life. Okay, so the way I look at human sensing is the device-free human sensing is you have the signals of opportunity, and you can actually sort of have ambience intelligence based on these signals, and then you use them to sort of sense subjects and interpret various things. Okay, so I have here I've laid out all the options that you can generally have, and I'll quickly go over them, and then I'll probably go into some detail of some of these. So the first one is vision based. So to be honest, if you can ensure that there are cameras everywhere, there is clear line of sight, then the problem is solved. Okay, our computer vision technology has improved and is at a stage where if you can actually have cameras, you can very precisely sort of count how many people are there. Of course, whether somebody's there or not. You can count, you can, by facial recognition or whatever, you can recognize who those people are, and then where they are, and then what they are doing, all sorts of things. The problem is you are not going to get people to agree to have cameras in residential environments. It's good for surveillance, but you actually cannot say somebody, what, I'm going to set up a couple of cameras in your living room, some in your bedrooms, in your corridors, and maybe even in bathrooms. You're not going to go anywhere with that, even though the technology is fantastic. But because of privacy, you cannot really sort of use cameras for most of these applications. So basically the whole point is you cannot invade privacy, but you want to provide service. And then there is this group of technology, and I'll quickly go over one by one, but essentially the subject is the agent of change. So that means I am present in a room. So think about visible light. So the crudest way you can explain visible light and the impact on that would be I'll be casting shadow. So and again, if you think about radio frequency or wireless, then I being present in a room, I can either obstruct the wireless signal, I can offer myself as a reflector, and that way I can probably aid in wireless signal propagation, but that means I am changing the propagation environment. So that change can be measured, and that change can be mapped to somebody's position or somebody's activities or whatever. Similarly, I being present also impact the electric field, and if I can measure that change, I could use that to my advantage. So those are the three ones where a subject being present in a certain location changes sort of creates these changes. And then there are certain technology where the subject is the source of some signals. So when we walk on the floor, we are creating vibrations. So if you have sort of seismic sensors, you may be able to pick up those vibrations, and based on that, maybe you can count people, maybe you can position them. If people have different type of sort of cadence and different characteristics in terms of how they walk, then maybe even you could identify people. Okay, and then the other one is we as human beings, we emit um, infrared, and if you can capture that, maybe you can use that for human sensing as well. Okay, so there are many of these opportunities, and with Internet of Things, a lot of these sensors that can pick up these changes or pick up these signals can already be present in the environment. So my thinking always is, how can you leverage pre-existing infrastructure rather than saying, oh, you have to set up a completely new system. You basically say, you have a building that has wireless network, you have a building that has a lighting network, you have building that has power lines. By the way, the building has seismic monitors and things like that, and motion detectors. Okay, so how can we, sort of combine all of that and sort of, leverage that for human sensing applications? So they have their primary use for something else, but can we get a secondary service by having all of those? Okay, so that is the GPS ethos. There is infrastructure. Can we use that? So the most heavily investigated technology is based on RF. People started investigating that because it also sort of kind of has the advantage that maybe you can use existing Wi-Fi network. Okay, the problem is unless you have a very bespoke system, in most cases they are the least robust and least accurate. Okay, so but the whole premise is that a subject alters the wireless channel, and that channel, that change that subject is creating by being at a certain location and performing certain activities, or being at a certain location and having a certain number of subjects, you could map that to these things. So whatever the change is, you map that to a subject being at a location performing some activities. But this is the most sort of heavily investigated technologies. A lot of sort of papers are out there. So if you are new to the field of human sensing, this is the most difficult sort of area to get into, because this has been heavily investigated, and it has been so unless you've been working on this for a long time, it'll be very difficult to get traction in this, because you have to do something that is very complex, and you have to sort of catch up to a lot of development that has already been there. Then the next one that I wanted to sort of talk about is infrared based sensing. We do emit infrared, and there's a very simple way of picking that up. So we have these things, motion detectors that are oftentimes used for security purposes. So it works on a very simple principle that it actually has just two sort of, let's say, pyroelectric element. So when we cross sort of like the field of view of that element, whatever infrared we're emitting, that gets registered in that sensor. Okay, so by having two elements connected to the two inputs of a differential amplifier, what happens is if somebody is walking like that, that person is first crossing this one and then crossing this one. So then because you are sort of inputting this into a differential amplifier, you get an output like this, or you get an output like that. Okay, and most motion detectors, what they would do is they'll basically say, yep, somebody is present because I have a voltage level and somebody is present. So if you are stationary, nothing will happen because you're not crossing this. So these things cannot really deal with stationary sort of subjects. So if you just use this, then you can probably do a lot of fine graining, because if you have ever seen a motion detector, they actually have something called the Fresnel lenses, and what they do is they narrow the field of view. So you have very narrow sort of field of views. So when you're crossing, you don't have to cross a lot of area. If you cross a little bit of small area, you register at that plus and minus, and then you get picked up. So what people have done is, by having many of those, you can try to localize somebody, because this motion detector is saying, oh, I see a movement. This is saying I see a movement, and this is saying I see a movement. So of course you have to be somewhere in the intersection. And if this is fine grained, then probably your localization can be reasonably good. What people have started to do now is, rather than using it, what they are doing is they just go here and say, okay, I'm going to look at what is the level of output, rather than saying, oh, somebody just crossed this. Can I actually sort of map whatever this output is coming out of this PIR sensor, and map that with somebody's position or somebody's activities or something like that. And people have also tried fusing this with various other sensors. So this is MIT's Media Labs, the so-called chameleon sensor that actually has a PIR sensor like this and a CO2 sensors. And using that, they were trying to sort of understand what activities were going on in a lab or in a classroom and things like that. and if you're interested, you can read this paper. So the other way you can use IR or infrared based sensing is using thermopiles, which are actually very low resolution thermal cameras. So if so one of my students in front of a reasonably high resolution thermal camera versus an 8x8 thermopile. So you can see that here you can pick up some features, and that can be problematic, whereas this is pretty much there is nothing of that a human can see from here. So one of my students standing here, um, you know camera, of course, he'll look like that, whereas with a thermopile you look like that. So that way you can say this is not really very sort of privacy invasive. Now if you want to track somebody, what you can do is you can try to track this blob, and there are other things that you can do if you have this information. So I'll give you some example just a little later. So we what we did was we made these sensors, and they are made out of Panasonic grid eye sensors, 8x8, and based on that we tracked a subject within a certain area, and they were quite accurate. What we did was we basically sort of used machine learning to sort of train some combination of convolutional neural net with LSTMs, and sort of got reasonably good accuracy out of this. And you can clearly see that we are not sort of getting a lot of sort of features out of this. So this is not really privacy invasive in that sense. Another example is fall detection. So one of my students sort of having fall poses here versus sitting and standing, and there are 6 thermopile cameras that are actually sort of capturing that. And if you are if you have trained, so what we had is we had 15 subjects sort of doing these activities, and then we use that data to train so we used 5 subjects data to train some classifiers, and then we tested that on the other 10 that we did not sort of use for training, and we are getting reasonably high 95% plus accuracy when we are trying to recognize within these activities whether somebody has fallen down or whether somebody has not fallen down. Okay. But it's not as simple as it sounds. So unless you are very, very careful, so you can see that a human being registers as only 1 pixel. So somebody is standing, and there are 6 thermopiles, and this person is actually standing kind of in the overlap of 4 of those, and that person is being registered as only 1 pixel. And what we found out was you need to be careful about what the height of the ceiling is, and also what cabling you are using, and so there needs to be some sort of a sort of thinking behind it, because if you are just registering as 1 pixel, one snapshot is not going to give you anything. Okay, it's pretty much hopeless. So you have also electric field sensing. So it is kind of a subject being here will change the ambient electric field, and you can sort of pick up this change by using electrical potential potential sensors, electric potential sensors, and based on that, what you can do is when whatever change you are seeing based on somebody's presence, you can map that to whatever it was, maybe somebody's position or maybe somebody's activities or something like that. And based on that, it has mainly, I've seen this mainly for localization. There was one very interesting paper that came out of, I think, Carnegie Mellon in the US, and what they were doing is, so if you are in a room, you are also kind of getting coupled, some sort of a capacitive coupling based on electrical field with the power lines. So we have power lines inside the room, because of course electricity. And what they were doing is, because you are coupling, so what they did was they had bespoke transmitters and receivers on the power sockets. So the transmitter is sending a high frequency sine wave through the power line to to a receiver, that is also on the power line. So this is almost like power line communication. But depending on whether somebody is present or not, you are actually coupling with the power line. And so the impedance of the line is actually changing. And depending on where you are, that change or that load that you are presenting actually changes. And they map that and try to localize. Very clever idea. And so that is just an example. There are many examples of electric field sort of based sort of sensing. The one that I want to spend a little bit of time on is capacitive floor. So basically the idea is your foot is one plate of a parallel plate capacitor, and the floor, underneath the floor, you have some sort of a conductive material, and that makes up the other plate. So you and the flooring creates a parallel plate capacitor. And if you have that, then what you can do is you can try to read that capacitance. So basically it is literally you are trying to read the RC time constant. So what you can do is you can either have a capacitive sensor like a proximity sensor, but what we do is we basically try to toggle between low and high between sort of two pins of a microprocessor. And by doing that, you can actually sort of pick up somebody's presence on the floor. Okay, so this is an example of a capacitive floor that we made. And so this is somebody who's walking across the floors. Okay, and you can see that how they put their feet, you can kind of also try to measure that, so you can maybe get some gait information, how what's the stride length, what's the cadence of their walk, how how do they place their foot in terms of so with respect to the direction they're moving, how do they transfer their sort of foot from the heel to the middle of the foot and then to the toe and then push off. Okay, this is the same floor, but these images are captured when somebody is lying on the floor. Okay, so based on that, I have a small video of this working. So I'll try to maybe I think I've done more damage to this than yeah. So if you look at this video, so one of my student is, so this is a small version of the floor. So if I just pause that here, what you can see is, so the orange line that you see is actually whatever is on his head. So this is a virtual reality HTC Vive Park. So we are tracking them using these lighthouses. So this is just the ground truth. So the floor doesn't use that. So, but the orange line is basically where the HTC Vive system says this park is. So that is what this orange line is tracing. And the process that you see here, those are basically what the floor says that person's foot is. Okay, and in this computer you can see that when my student is walking, you can clearly see those blips here. So those are his positions, in terms of the where he's putting his sort of feet. And then the other example of that floor is when somebody is lying down, you can clearly see that person's sort of image on the floor, because this is almost like sort of like a touch screen. Okay, and currently we have a project running that has received reasonably large funding. So we are trying to commercialize this technology, and so that you can. The idea is, if your floor is like that, then rather than sort of monitoring you by asking you to come to the doctors, we are monitoring somebody's activities in their home, how they're walking, whether their gait is changing or not. Of course, if somebody's fallen down, you can pick that up. But if we can realize that somebody is walking and then little by little they are getting frail and their gait is changing, then maybe you can sort of tell the doctor that maybe this person has hidden pneumonia, or this person has become too frail, and that person is at risk of suffering a fall in the near future. Okay, so the idea is, sort of prediction and making sure that we can sort of take some sort of a countermeasure before an incident happens. Okay, so but this is not in a clinical environment. So the idea, oftentimes, your gait changes because you have some sort of an onset of a disease like an Alzheimer or something like that. So and your gait starts to change. So if this is basically your floor in your living room, in your bedroom, and you're walking there every day, then what we may be able to tell is, your gait is changing. Now the question is, why is it changing? Okay, and maybe we can take some actions right after we realize that. So this is another example of human sensing, but this is based on visible light sensing. So what we have is here we have 7 sensors on a wall, and a person is standing on various locations around that wall. So what you see here is what this light sensor is seeing in terms of its light level or illuminance, okay, when a person is at various locations. So this is one of the photodiodes, one of the photosensors. This is what this photosensor is seeing. This is what this photosensor is seeing, so on. And each of these is basically when somebody is here or here or here or here, this is what the light level is at this sensor. So at some positions, you make a massive difference for this photosensor. Again, for another particular location, you make a massive difference in the light level for this particular sensor. And by sort of taking some data, we actually could track somebody walking across this test bed very accurately by just sort of looking at how the light level is changing across these sensors. Okay, so this is but there are a couple of papers that we published a few years ago based on visible light sensing. So now what I want to do is I want to give one more example, and then sort of want to conclude with some ideas about what needs to be done. So this is an example of a vibration-based sensing. So vibration-based sensing is you have seismic sensors or something like that, and you are walking on the floor. So you are creating vibrations. So if we can sort of find the time difference of arrival. So basically, what is the, when do I pick this vibration in this sensor and this sensor? So what is the difference between the vibration arriving at this sensor versus arriving at the other sensor? So if you have that time difference of arrival, you may be able to localize somebody. There are some papers that I've seen where they have used this technology to identify people. There was one paper that came out where they were trying to recognize whether somebody has a disease like a muscular dystrophy or something like that, based on this. They're very, very exciting, sort of type of work. So their idea was, you are walking to the doctor, so you've gone to the doctor's chamber, but you have walked all the way to the doctor, and based on how you've walked and what they picked up, they may have picked up a lot of about your gait and certain things about you by the time you have gone to see the doctor. So out of all of these things, what needs to be done at the moment? So one problem that we currently have is the calibration. So all the systems that you've seen, they work really well in controlled environment. So you can actually calibrate this to the nth and have a very good sort of performance, very sort of accurate, doing what it's supposed to do in a controlled environment in a lab. But you take it somewhere else and it's not very good. I always sort of tell my students and other colleagues that if you create a human sensing system, give me about 5 minutes and I'll break that, because I know that you have fine-tuned that to so it's very difficult to generalize at the moment. There is most of the systems that I see, they are calibrated to a certain location, and it's not very easy to calibrate this to another location. Okay, so that is something that needs to be looked at. If you're using machine learning, what sort of transfer, learning can be used, so that it's not a training from scratch again. Privacy and security, I haven't really seen a whole lot of sort of discussion on privacy and security, other than, oh, cameras are bad. So but we are actually sort of looking at very personal information. What is somebody doing and who's that person? And also there are a lot of edge devices here that are connected by wireless. So that's a recipe for privacy and security breach. So it needs to be. So we know that network security is something that people have looked at for a long time. Okay, however, from this perspective, when somebody is proposing a particular system, it is very rare that system gets investigated in terms of its robustness, in terms of security. Okay, so that is something that really needs to be looked at. Application of machine learning nowadays, that is what everybody is doing. I have a problem, I don't really understand it. What I'm going to do is I'm going to apply machine learning to it. I know what the data is, I know what I want, and there is my big black box, and I'm going to solve this problem using machine learning. One of the challenges with machine learning, of course, is training corpus. You need a lot of data to train a machine learning algorithm. That means a lot of time, a lot of resources need to be there. So one way you can help this discipline is if you have a physical system that you've built, rather than keeping the data to yourself. Once you have written your paper, make that data available to everybody else, so that someone else can use that data and come up with an algorithm. Okay, and there are papers that do not sort of do anything other than have collected data, and then maybe ran a very simple machine learning algorithm and made that data available to everybody, and say, why don't you sort of do better? So just collecting data and making sure that this data is available is going to be a big help. Now there are some data, already public domain data, available about wireless human sensing, and with instrumented, sort of like if you have accelerometer or something, instrumented, there's a lot of data. There is some data there, but things that I've shown here today, you're not going to get a lot of public domain data. So if you can just, even if you're not designing very complicated algorithm, if you have a physical system and if you collect a lot of data, and if you can make the data available, that itself will be a major contribution. Then sensor fusion is one thing that I'm very passionate about, because what happens is people look at this problem and then they say, okay, I'm an expert in wireless technology and I'm going to solve this using wireless technology. The problem is, for any particular technology that you want to use, you're not going to have many of those in a house. So if somebody says, oh, I need you to break 10 RF link so that I can sense you, your question would be, how am I going to get that many links? I have only one Wi-Fi system and maybe a few devices. Oh, I so the question is, but if you have a couple of sort of wireless devices, if you have a few motion detectors, if you have a seismic sensors, okay, can we combine all of that to actually get a more robust system that is more practical? So you already have this, and then you say, okay, I have a little bit of gap in coverage, or a little bit of sort of lacking in information. So can I interpolate that, or can I actually use some sensors just to supplement this? So rather than trying to solve this as a single sensor problem, try to solve this as a multi-sensor problem, where so that it becomes more practical. Okay, so that you're saying, these networks are already available, these sensors are already available, let's fuse that and then see whether we need anything else or not, rather than saying, oh, you need 20 wireless devices, or you need 6 motion detectors in a room. Why would you need, for security purposes or for controlling light, you're not going to need 6 motion detectors, but for gesture recognition, for activity recognition, you need 6. So that means you need to bring in 5 extra motion detectors, and then it falls on its face. That means investment. So the idea would be, rather than calling for that, there is a vibration sensor because this building is being monitored for seismic, sort of, like just like a earthquake monitor or something like that. Can you use that? There is a Wi-Fi link. Can you actually use that? Okay, rather than saying, oh, we're going to have impractical number of sensors because we need to build this system. Then two other things. One is most of these systems are designed for a single subject. So every extra subject is creating interference in the environment. Of course, in a room you're not going to have a lot of people, but most of the human sensing systems that I've seen, they always do this. They say, we have done this for one subject. Multi-subject is a problem that we will investigate in the future. Very few people actually investigate that in the future. They move on to something else. Or sometimes maybe there are two subjects, and then it's that's the extent of it. To be honest, probably you don't need to, other than when you're trying to count people in an evacuation environment, in a scenario. In most cases, probably you need to have 3 or 4 subjects, no more than that. So, but people stop usually at 1. And the last one that I wanted to talk about is the need for having system that can operate in real time. So in most of those systems, what people do is people will collect a lot of data and then separate that data into a training sort of corpus where they train and validate their system, and then they will test on a testing data set. But all of that was collected at the same time. I haven't really seen a whole lot of example of sort of a human sensing system that is operating in real time. There are, but usually they are not. So if I just go back to this system, this one, in this demo, we actually had a system that was working in real time. Okay, but very rarely I've seen a system. So you can clearly see here that when my student is walking, you can clearly see that is getting sort of tracked. But very rarely we actually see a system where the system is operating in real time. So that is the next thing. I think when people would basically say, not only we have a robust system, this system will actually operate in real time. Okay, so that is where I actually want to stop. There I want to acknowledge some of my recent PhD students. Nathaniel, Baden, Daniel, who graduated from my lab and currently working at various sort of uh, R&D institutes. And Eric and Jasmine are still with me, and and in all research, I'm the tip of the iceberg. I am speaking here, but a lot of people's work actually went into all of this, and I'm thankful that I got the opportunity to work with these brilliant young people. If you want more additional details, there is a review paper, but this is mainly focusing on localization. You can have a look at that, and of course, I'll be more than happy to take some Q&A right now. And if you want to sort of know more or want to collaborate, research and academics, we are collaborative by nature. So that is my email address, and I'm happy to take any questions that you may have.
Thank you very much, Professor. And if you guys have any problem, please feel free to drop in the chat box, or you can let us know by unmuting. So the panelists can ask questions by unmuting themselves, but the attendees can send up their questions in the chat. So there are a few messages on the R10 account privately that request the slides for the session and the recording. So I hope if Professor Fakhrul is okay to share it with the participants.
Yeah, I'm fine. If just make a probably a PDF. That'll be much easier because this file itself is about 100 megs with videos and things. So that's not very conducive to sharing. So if just make a PDF, most of these are actually in various papers that I wrote. So there's nothing secret.
Well, yeah, we yeah, I think we have one question. Yeah. Sorry. Can you please say something about international interaction where humans seek attention and to interact with sensors? Where is this technology at? It is in the chat box. That question.
So is it something like yeah, so that is there are as I said, if you use a camera, then there are a lot. But if you do not use camera, then it's as I said, people are trying, but fine-grained things where you want to interact with a machine or something like that, it's not that's a very fine-grained sort of recognition, and using what we are showing here. Probably the technology is not there as far as I can say, but using camera or anything that is in that field, you can do it. It's not a problem.
Hi, Professor.
Hello.
Yeah, I have some clarification.
Yeah.
Okay, so this is about this is about the I think you mentioned about controlled environment, right? So I'm just curious about this time the non-controlled environment setup. Is it still site specific? I mean, is it dependent on the dimension of the room or the house or the home?
Yeah, so most of the technology that you see, at least in the papers, they are very, very well calibrated to a particular environment. So one of my goal is to sort of think about what would be a practical system. So somebody does some sort of a calibration in the factory, right? So they have calibrated the system, and then they say, okay, we come to your house, we're going to spend 5 minutes. Either you walk around, or you do some activities, and then the training goes to that level where most of the training was already done in the factory, and now we can calibrate that for you as a person. The problem is, right now, the way I see it is you almost have to do the whole training from scratch.
Yes, I
So
agree.
so in most cases, that is what it is. I've seen papers where they've said, oh, we've done transfer learning, and by the way, look at this. But even those are, I would say, questionable, in the sense that I think they are still going from one controlled environment to another controlled environment.
Yes, I
So
agree.
yeah.
Even the fixtures, I believe, will affect
Yeah, just
the
think
house
about the
fixtures.
vibration, right? Think about the
Yes,
vibration. The floor is a
agree.
non-homogeneous medium, and then the vibration would be very, very different if you go from one building to the next.
Yes, I agree.
So
Yeah.
a lot of that. So yeah. But it comes back to this. People will always say, look, there is already technology out there that can do better than this. I'll say, yeah, fantastic. But it's kind of like, oh, there is already vanilla ice cream, so there is no need to have any other flavor. Whatever technology is out there right now is good because a lot of people put a lot of effort into it. So your technology at this moment is not probably on that level, but give us 20 years and a lot of brilliant minds, and probably that technology would be as mature as, I don't know, as a LiDAR or something like that. It is all about how many people actually gets excited about this, and try to solve the problem. I mean, when humans put their mind to it, people actually went all the way to the moon, right? So it's all about, you know, sort of how much effort you do, and
Yeah.
whether there is a need for that or not.
Hey, Warren, I think there's still some
Look, I
questions in
mean,
the chat
if
box.
I cannot answer them now, you know, you can just compile everything and send me an email, and I'll try to go over them, and more than happy to, you know, sort of go back.
Yeah, we have a few questions coming up in the chat box, Professor, if you would like to take them.
Yeah, that's fine. Can I see them?
You probably can check the chat. And, maybe I can read it out to you.
Let me try to. It says closed
Okay.
chat, so which was not very helpful. Yeah, I'm sorry, I cannot see this. See the chats. I'm sorry. So if you can read them, that's fine.
I will read it to them
Okay.
to you.
Yeah.
So, first question is that how do we differentiate between person A and person B? That is reference to what was discussed earlier.
Depends on the system and how different those two persons are. Sometimes if you know, people have different height, different weight, different BMI, and then they are walking you know, everything is very different. So in that case, if there are a lot of distinguishing features like that, and if you have a system that can pick that up, so for example, like a floor, that can probably, if you're walking, that can probably pick out a lot of gait information. So the floor that I showed you, using that floor with 24 people walking on that floor one by one, we actually were able to recognize after training with a 97% accuracy who was whom. And we were also able to tell, you know, whether somebody was you know, sort of like a cisgender male or a cisgender female. So it can be done, but the thing is, you know, it really depends on the system. And one interesting thing that we found out was there of the volunteers, there were two people, you know, who were roommates, and our system had a lot of difficulty recognizing those two, and they were you know, similarly sized. But one of the things, because they lived in the same apartment, I thought that maybe they got used to walking very, you know, in a very similar style or whatever. Our system had a lot of difficulty recognizing between those two, but for everything else, it was reasonably simple. But again, it really depends on systems. I have seen you know, systems really struggle to identify who's whom. So one of the major problems that you have is the crossover. So two persons are walking, and they meet, and then have they gone back like this, or have they actually crossed over and gone like that? A lot of systems actually break even for a simple crossover event. So it really depends on how much of training you have and how distinct are those people. And some systems are reasonably okay, but I would still say, yeah, it's not has been solved, you know, very robustly.
Thank you, Professor. And we have some more questions. So,
Yeah.
please comment on face recognition for security purpose. So,
Yeah, I mean, to be honest, if you can have camera and you can have facial recognition technology, then it's fine. I mean, in many business premises, it is, you know, sort of the condition of entry is that you will actually have to pass through that camera. So in New Zealand currently, they are trialing facial recognition technology in supermarkets, and there's a lot of, you know, sort of currently comments in the newspapers about, oh, is that an invasion of privacy or not? But you know, facial recognition technology is pretty mature, and you can recognize people using facial recognition technology. That has been there for a long time for surveillance and other purposes. You know, it's been there for two plus decades. But what we are talking about here is you cannot use a camera. It's kind of ironic that, you know, we have cell phones, and all the cell phones have cameras. We have, you know, PlayStations and whatnot, they all have cameras. But then as soon as it comes, we want to give you some service, people say no cameras. So The whole point is, you cannot use a camera. You cannot use vision for these applications. These are non-computer vision, non-contact less. So wearable. So I saw a question, briefly come about sort of wearable technology. The wearable technology is fantastic if somebody is wearing them. There's a stigma, you know, especially with older adults, when basically you're saying, what, you have to wake up every morning and then you have to get this bracelet on. And a lot of the accidents actually happen during the evening when somebody has retired, and then they have not really, when they've woke up and maybe going to the bathroom or something, they are not going to sort of put that sort of sensor on. And that is when a lot of the accidents happen. That's one thing. Second thing is, maybe you are trying to provide service to somebody who's already forgetful, so that person has not really remembered to put this on. Or then maybe they want to put that on but they forgot to charge that. So those things needs user intervention. Those things need active cooperation from the subject. And if that person is actively cooperating, then probably that person doesn't need a whole lot of help. It is about sort of giving help to people who are not capable of probably asking it actively, and they are also not very happy about sort of having cameras or some sort of a thing that can tag and trace you. So it's a so some of the projects that we do, we have this issue where all I could say is, only if I could put a camera there, or only if I could make sure that you were wearing your Apple Watch. But the problem is, even the simple thing, in New Zealand, what they have is something called a personal alarm system. So you have a lanyard and then you have an alarm. So if you have an incident, you can actually press that alarm and then an ambulance could come. First, they will try to talk to you, and then there would be so it's a subscription based service, and it's subsidized. But even that is a problem, because either you've forgotten to wear that, or you fell down, you are in a confused state, and you don't have the wherewithal to actually press that. So those technologies are fine, but it's very easy to be in a situation where that technology is not with you, if that makes sense. Yeah.
Um, Thank you very much, Professor. I think there are a few more questions coming up. So, with the time, we'll stick with one more question.
That's
So,
fine. And as I said, my offer still stands. You can compile them and send me an email. I'll try to reply back.
yes, thank you very much. And one last question. Can you please comment on wearable and contactless sensing? And is contactless sensing will be prominent replacing the wearable sensing?
Well, it depends on how good it becomes, right? I mean, during COVID, one thing we found out is touching something is not good. So one of the work that we did, and I have not really mentioned this here, is contactless gesture recognition. But with contactless gesture recognition, one of the problem is dynamic gesture is inherently easier because you are actually causing a lot of change by doing this. But if it's a static one, then a lot of the systems actually, there is nothing changing. So sometimes the static one seems to be the simple one, but systems struggle with that. So there people are working on that, and I believe that first of all, if the technology is not robust, then no one is going to use that. So it has to go to that level, and that is the whole point at the moment, is trying to get the technology to a level where it can be as good as a contact, as a wearable. So in controlled environment, we have reached that point, but in a uncontrolled environment, it's not there yet. And to be honest, I have doubts about wearable sensors as well. So for example, you sneeze and sometime your watch will think that you've fallen, because the accelerometer has actually sort of recognized something that was very violent and very quick. So it's not like every technology is bulletproof.
Thank you very much, Professor, for answering all the questions. I think now will there are a few more questions, so we will compile them together and send it to you so that you
Absolutely.
can leisurely answer those. So thank you very much for the insightful session. So thank you very much, Professor, for that enlightening talk. And we trust that each of you have found valuable insights to take away from it. And now it's time to invite, it's my pleasure to invite Professor Jennifer De La Cruz, the Student Activities Committee Chair of IEEE Region 10, to deliver the vote of thanks for this session. Professor
Thank you,
Jennifer, over
Aru.
to you.
Yes, I hope you can hear me. Yeah. Good evening once again, everyone, especially to our dear speaker, Professor Fakhrul. Thank you very much. All the participants in and outside Region 10 and the vibrant organizers of R10 Talk webinar series. So it was an evening of interactive and insightful session about indoor human sensing. And we learned the convenience of device-free localization and how different sensors can be strategically positioned to monitor and extract information on whether there is a warm body or not. So from the basic PIR sensors that we can use for human sensing to thermopile sensors, detecting warm bodies, and interestingly, using electric power steering and designing a capacity floor to detect the presence of humans. So in conclusion, human sensing technology plays a pivotal role in the evolution of smart homes and smart buildings, offering a myriad of benefits in terms of convenience, energy efficiency, safety, and of course, comfort. And through the integration of various sensors, as Professor Fakhrul has mentioned to us, and utilizing advanced data analytics, well, these systems can adapt to the needs and preferences of occupants in real time, enhancing our overall living and working experiences. So it was incredibly an interesting talk, Professor Fakhrul, and personally, I have loads of takeaways. And yeah, I'm truly glad that I immediately approach you and take the opportunity to invite you to speak to R10. And with that, on behalf of our R10 Director, Professor Lance Fung, and R10 Talk team led by Dr. Zia Ahmed, we thank you for your time and effort. And we appreciate your support to Region 10, and we are truly grateful for sharing your distinguished engineering expertise to R10. So everyone, can I request everyone to give Professor Fakhrul a round of applause? Thank you. A virtual round of applause.
Thank you.
Thank you. So we also thank our dear Miss Waronika Hipola, so my lifeline, our region student representative for moderating this third 10 Talk for this year. Thank you, Waru. Thank you very much. Over to you, Waru.
Thank you very much, Prof. Jen, and thank you very much, everyone, for your active participation. I think it was a really good session where we had a lot of interactions, and even there are a lot of participants. So I think this is a successful session. So as we are coming to the end of our session, now before winding up, I would like to get all of your feedback on our session so that we can improve our webinars in the future. So please scan this QR and go to the form and provide your honest feedback on our sessions. So the R10 Talk webinars will be more productive and more effective in the future. So thank you very much. And also, be with us and keep in touch with us to get information about upcoming webinars. So our next webinar in May will be navigating corporate career as an entrepreneur. So this will be presented by Huzeb Shafi, and he is a solutions architect in smart cities and business and business process automation at Cisco. So this will be in May, and the time and the date will be informed later. So stay in touch with us. So these are the committees who has supported and who has collaboratively put effort on the success of IEEE Region 10 talk. So thank you very much, everybody. And so we will connect with us through these channels, and we will give you the information on the upcoming webinars. Also provide your feedback on what are the topics that you would like to discuss under Region 10 Talk. So with that, thank you very much, everybody.
I think we can also have some,
Yes.
have a short follow-up with Professor Fakhrul.
Yes. So with that, let's wind up the session. Thank you, everybody. And I will invite the panelists to stay for a small group photo as a memory. Thank you very much.
Who's going to take a picture? Thank you, Professor.
Yeah, thank you very much for a nice talk.
Yeah, it was fun.
Yeah,
Yes.
thank you.
You know, I remember Professor Lawrence Ong, the former director. He used to talk about localizations. Yeah, he used to talk about localizations. It's the first time I learned about localizations, indoor localizations. It's from Professor Lawrence.
Yeah, that is where it starts pretty much, and then you know, people have gone into more fine-grained sort of activity recognitions and things like that. To be honest, when I started around 2016 in this field, I was mainly doing localization for about 3 or 4 years, and then eventually sort of moved into hand gesture and other recognition and occupancy counting and things like that.
But he focused on Wi-Fi, like getting footprints from access points.
Yeah, we've done a lot of that, to be honest. But as I said, I'm not married to a technology in the sense that, and I want to solve the problem, and a lot of these technologies, we had to learn ourselves because, especially vibration and things like that, those are mechanical engineers domains. So we have an expert who does acoustic signal processing, and we are actually working with him on the vibration based ones. It's to be honest, I believe it's a multi-sensory problem. Otherwise, you only sort of get to solve only part of the problem.
I agree. So there's one advisee of mine who attended, and then he said, "Mom, I got a lot of information from this, and I'll probably start from here." So thank you very much. So who's going to take a picture, Waru?
Let's take a picture. I'll take from my
Abina, Abby, do you want to join? Abby, can please join us?
Abby, are you in a place to open your camera?
Okay, so maybe we can just take the picture.
Let me check. 1, 2, 3.
Okay.
Thank you.
Thank you.
Thank you, everyone. One more?
Oh, okay. I'm good. Yes,
Good.
we are good. Okay, Prof. Chen. Thank you.
Thank
you
you so
very
much.
much.
Thank you, Prof.
Okay, thank you very much.
Thank you, Prof. Aki.
Thank you. Yep.
Thank you, Prakash sir. Thank you, Prof.
Thank you very much,
Thank you,
Professor Fakhrul Alam. Thank you, Jennifer. Thank you, Professor Aki. Thank you,
Yeah, thank you so much for
Bye.
hosting me. See ya.
Yeah, thank you.
See you on TPIC.
Yes, it will.
Yes. Bye-bye.
Okay, bye.
Bye.
Okay.